So the hypothesis of continental drift led into the theory of plate tectonics. And the theory of plate tectonics is that the Earth's crust is made of plates and that the plates move. Very similar to what the hypothesis of continental drift, but the main difference being in that in continental drift, Alfred Wegener thought there was only one supercontinent and all the continents broke away and drifted from there. The theory of plate tectonics involves many times that there would have been supercontinents and that the continents are constantly moving around. So that's the difference in that movement part. In continental drift, it was only one time that they were together, and the idea of plate tectonics is that they've been together multiple times and moved apart. And we've got two pieces of evidence that we're going to go through, and that is seafloor spreading and paleomagnetism. So first of all, what is seafloor spreading? And then we'll talk about how it actually proves that the theory of plate tectonics is true. So seafloor spreading happens because there's different temperatures in the center of the planet. So the core, when we looked at the layers of Earth, and you talked about how hot the core was, that's the hottest part. And we know, because of laws of physics, we know that warm things rise, right? Warm air rises, warm water rises, and warm magma is going to do the same thing. It's going to rise from the area where it's hottest because it's less dense than the surrounding material. So it's going to rise up from there until it gets to a point where it cools, and then it's going to sink again, just like warm air rises until it cools and then it sinks again. This is called convection. And it happens in water, it happens in the mantle, and it happens in air. So as that magma rises, it's going to run into the crust. And when it does, when it bangs into the crust, it makes it move and it separates it apart. And so that's why you've got these arrows pointing. So the magma is rising up, it runs into that crust and it forces it out to the side. And it makes a break. It makes a ridge. In this case, a ridge is, it's a little bit of a mountain, but mostly it's a rent or it's a tear in the crust. That's because this is where the magma is warmer and it's rising up towards the surface. So new crust is getting created in this area because as the seafloor gets pushed apart, the magma comes up, it cools when it gets towards the surface, and it hardens into rock. As it pushes it, the oceanic crust, or that stuff that's underneath the ocean, is denser than the continental crust because it's got the weight of the oceans pushing down on it and pushing all those particles closer together, and so it's denser and heavier than the continental crust. And so when that oceanic crust runs into the continental crust, it pushes underneath it and takes a dive underneath it into the mantle. And so crust is destroyed there, right? Because we said that as the crust gets pushed down and heated up, we talked about the rock cycle, it's going to melt it back into magma. Our planet's not getting any bigger. So if we're making new crust in the center of the ocean, we've got to be destroying it somewhere else because the whole planet's staying the same size. So seafloor spreading is just that idea that magma comes up, it's pushing the crust to the side, and new ocean floor is being made. So this is what I was just saying. So as you're filling in your notes in your flip book, you should be on that page for seafloor spreading and paleomagnetism. These are the steps in seafloor spreading. So the magma is rising up, it's forcing the crust apart, magma fills the gap, it hardens and makes new rock. If you need a little bit more time on this slide, go ahead and push your pause button until you got what you need in your notes. So as a result, we get new ocean crust. So the result of seafloor spreading is new crust at a mid-ocean ridge. The ridge is where the crust is made. The trench is where it's destroyed. The ridge is in the middle, which is why it's a mid-ocean ridge, and the trenches are near the continents. There is one ridge that goes through, well, there's a couple of ridges actually that go through land, and we'll look at those examples here in a minute. So our oldest crust is by our continents. One of the things we know from seafloor spreading is it's going to tell us the age of the ocean floor. If the rock is hardening at the break in the crust in the middle of the ocean, then that's the newest rock. In order to get pushed underneath in the trenches, that rock had to have been there first in order to get pushed to the side. So that's our older rock, and that is over by the continents. So how do we know this is what it looks like? Because remember, we talked about with Alfred Wegener, people really hadn't been down to the ocean floor. They hadn't gotten much off of the continental shelves at all. So in the 1940s, sonar was used in World War II for the submarines, and they were using sound waves, and they were sending those sound waves out, and then they would ping off of one of the enemy ships. And what they would do to figure out the distance is that they would measure the amount of time that it took for the sound to move through the ocean to the ship and then back, and that would give them a distance of how far away that particular ship was. Well, in the 1960s, they figured out how to use that to map the ocean floor. So they've looked at the magnetic fields on the ocean floor, like the slide said, but they also use sonar to actually be able to tell the topography, or the ups and downs of the ocean floor. So we just didn't know what it looks like. They actually thought that it was nice and flat. They thought it was like a lake bottom kind of thing, but we know that's really not what they look like anymore. So in the 1960s, what they figured out was they're going to turn that sonar down, and they're going to start looking at areas in the Atlantic Ocean, and they started looking off the northeastern part of the United States and Canada. And what they found was stuff that they really didn't expect. So that was one way. That's with the sonar, and I'll come back to that in a minute. The magnetometer is a towed array, and so as you can see, here's your boat. Okay, and they're going to have this magnetometer, and it's just going to tell magnetic fields. It's like a magnet detector. Okay, it's a magnet, and it's going to detect magnetic fields. So when the rock comes up from the mantle and comes up through the mid-ocean ridge, there's iron in the rock. And when it comes up and it's still in its liquid state, it's going to line up with wherever magnetic north is. It's going to act like, they're all going to act like little magnets, and they're all going to line up north and south with wherever magnetic north is. And then it's going to cool down, and all those magnetic particles, all the iron in particular in the rock, is going to stay aligned with magnetic north. And what the result is this banding on the ocean floor that shows us which way magnetic north was when that particular rock was hardened, okay, from magma. And they use the magnetometer to tell which way magnetic north was when that rock was formed. And they can map it that way. Sonar is the other way. So sonar, once again, they're pointing those sound waves down, and they can measure the depth, and they can see where the mountains and the valleys and all that kind of cool stuff was underneath the ocean floor. And as a result, what they came out with was not flat, right? They realized that there are trenches, and there are mountains, and there are super deep areas that are, you know, deeper than any canyon that we have on the continental crust. They found taller mountains than what we have on the continental crust, and all this is beneath our ocean, so they didn't know it. So they found our deepest area is the Marianas Trench. It's really, really deep. You can see in here, here's where Mount Everest would be if you're looking in the Marianas Trench. How deep down, if you can't see those things, this is how deep down the Titanic is. But it's really, really far down there. So they just recently, within the last few years, actually made a submersible that could go to the bottom of the Marianas Trench. There's a Discovery Channel program that's about it. It's kind of cool to see. And they can see the life that's actually down there. When you think about the amount of water pressure that's pushing on any little critters down there, none of them have backbones, obviously. They're like jellies and stuff like that can squish with the water pressure. But it's really cool to think that there's actually stuff that lives that far down. So what do we figure out from our sonar and from our magnetometer is that we figured out that the age of the ocean crust changes. So the ridge, remember, is where the break in the crust happens. And like I said, that the rock at the ridge is younger because that's where the magma is coming up in the crack and forming into hardened rock. Our older rocks are over here at the trenches where they're getting pushed down because they became rock here, right? And then they had to get pushed all the way out. And see how it's kind of wavy in here, and that's because the rock is coming out. They're volcanoes. I mean, it's volcanic activity that's happening, and it's pushing it up. But as you get out here, layers of sediment start to fill in those holes and fill in those cracks in the rock and everything, and it kind of smooths it out a bit. You get thicker sediment over here by the trenches just because it's been there longer. So you're going to get more of your sedimentary rock on the ocean floor closer to what's called the subduction zone over here at the trench, where it's being subducted or pushed under the other plate. And you're going to find more of your igneous rock here along the ridges. We also found out that magnetic north changed over time. So seafloor, all these different mapping tools let us know how old the ocean floor was and let us know that magnetic north changed over time. Because we looked, once again, using that magnetometer, we could tell which way north and south was. And the study of this is called paleomagnetism. Paleo meaning ancient or old, and magnetism. So it's the ancient magnetism that's recorded in the rocks. And we can see where the changes have happened. We can see that they're not happening at the same rate over time. Each one, so this is where the mid-ocean ridge is at, right here. This is the mid-Atlantic ridge. Coming down here, we're in the middle of the red. And so that's the time that we're in right now, and that's the magnetism that we have right now. And each one of these colored bands shows us when it flipped. And you'll see how they're matching on either side, right? It may be a little bit lighter on one side than the other because more of the magma kind of went to one side of the ridge than the other, but you'll see how the pattern is mirrored on either side because the magnetism happened there. And we can tell how long then, because if we look at the rate of spreading that's happening now, using the principle of uniformitarianism, we say that the processes are happening the same way now as they've been for millions of years. And so we can look at that rate and they can start to say how old the rock is. So they're finding an age based on paleomagnetism, which is a more absolute age or an actual age of the rock, as opposed to the relative age of the rock, which is the, what distance are you? You're just further away from the ridge or you're closer to the trenches, that kind of thing. So magnetism on our planet is something that was one of the last lessons. So because the core, the inner core and the outer core are not the same consistency. The inner core is solid, the outer core is liquid. And as the inner core rotates and the outer core, they're not rotating at the same speed. So because of that, there's friction in between the inner core and the outer core. And as those iron particles that are within our iron-nickel core, both parts of it, they rub up against one another, and that's what's causing our magnetic field. Now, it's a little sci-fi-ish, but it's like our shield. And a lot of you talked about how this magnetic field is like our shield around our planet. And it does. It protects us from the UV light from the sun. It protects us from the solar energy coming in. It actually makes some of that kind of bend around us so that we don't get the full brunt of what's coming from the sun. It's one of the reasons why we can have life on our planet. The reversals happen. When the reversal happens, it's not that north becomes south and south becomes north, like the whole planet doesn't tip over. But I want you to imagine just this magnet. There isn't really a magnet in the middle of the planet, okay? It's just for visual. But it's kind of like if this were to flip over, okay? So it would just be that reversal, and no one has ever lived through a reversal. We can't really link any mass extinctions or anything like that to a magnetic reversal. So we're not entirely sure what will happen when poles reverse. We know that it probably will happen again because we can see that it's happened for hundreds of millions of years, that there have been reversals back and forth. We just don't have any evidence of what happens to life during that time. So once again, right, paleomagnetism is based on seafloor spreading. So it's the same process, right? That magma is coming up from the center of the earth, and it's coming up through the ridge. And the difference here, what they're showing you, is that paleomagnetic banding, or which way magnetic north was. So the lava is cooling, and all those little bits of iron are lining up with north, right? And then they cool. And when the rock cools, they're all lined up with which way north is. And then the center of that rock gets broken apart again, right? Because more magma is still coming up through the ridge and making more crust. And what we end up with, here's a little animation of our seafloor spreading happening. What we ended up with are these bands, and they named them, sometimes they name things based on some of the people who were the discoverers or stuff like that. That's usually where the names come from, are the people of the scientists. So it makes these bands, and then we can give a amount of time based on the current rate of spreading. Like I said before, it's the current rate of spreading, and then we see how much it spreads in a year. And then we can see how far away it is, and using math, then we can figure out about how old it is. And then they make maps of those, and they can show the ages on the ocean floor. So your red areas, so this one's like opposite. So here's your continents. Here's North America, right? Here's Canada, There's Mexico, South America. Here's the Mid-Atlantic Ridge. So the red crust is the youngest, and the blue crust is the oldest. So if you need to go back to anything, you can push the video back a little bit. You'll need to get your the parts of your booklet filled in.